All right, everyone, this is going to be a quick review on something we did a lot last year in AB, finding the particular solution when you start with a differential equation like one of these two, where you have x and y in your derivative, and you want to find the original function. So in other words, you're trying to get back to the point where you have y equals the original function in terms of x. So big key thing that I didn't do a lot last year, but we can talk more about this year, is a function or a derivative that is separable versus not separable. So if you look at this one, you're never going to see anything like this if I ask you to find the particular solution, because you can't find the particular solution using the process we're going to use, because there's no way to get the x on one side and the y terms on the other side. So for example, if you're like, well, can't you just subtract y? Okay, then you would subtract y over. Um, okay, and then what? Oh, can we multiply by dx? Well, if you do that, then you have dy minus, you'd have to multiply the y term times dx, and then you'd have x dx. And then, no, can't do it. This is called not separable. Can't separate this differential equation into x's on the right and y's on the left. So we will see these, though, in BC only, and we will do other things in the next lesson with them. But if I ever ask you to find the particular solution, the way you're going to do it is this process called separation of variables. The way it works is you basically get all the y terms on the left and all the x terms on the right. The first thing you always do then is you're going to divide or multiply. You never add or subtract, ever. So multiply or divide. That's your first move every time. You're never going to add or subtract anything over, because then you're not going to be able to separate the variables. So in this case, we're going to divide the y over. I like to write it like this. We're going to multiply the x over. Looks like this. So now we have separated the variables. Now we integrate both sides with respect to its variable. So on the left, y is the variable. We're going to integrate with respect to y. Sometimes this is a natural log. Sometimes it's a reverse power rule. Usually these are not too difficult of antiderivatives to find. So antiderivative of 1 over y is natural log absolute value of y equals antiderivative of x is 1/2 x squared, and then plus c. Do not forget plus c. This is called your constant that could be there, and we will solve for c pretty much every time if we are given an initial condition. So let's say there is an initial condition. The initial condition I want to use is 3, 1. So let's say the original function goes through the coordinate 3, 1. Then we can plug this information in and solve for c. Now, before we do that, this technically, if you get the y by itself at this point, where you e both sides, and you have absolute value of y. I'm going to ignore the absolute value right now. Talk more about that later. If you just left your answer like this is called the general solution. So, general solution. Typically, we don't stop at the general solution, but I don't know. There might be a case where they say just find the general solution. And that just means if you had an initial condition, you could plug it in here and find the particular solution for that given initial condition. But we are going to use my initial condition and find the particular solution. So I'm going to come back to this part, and I mentioned this a lot last year. I think you should plug in the initial condition before you solve for y, because it'll make the problems a lot easier. These are designed to be plugged in prior to solving. So that's my advice to you. So plug in the 1 for y, plug in 3. I'm going to change it. I'm going to make it 2, just so we don't deal with fractions. Plug in 2 for x. And we get natural log of 1 is 0 equals 2 squared is 4 divided by 2 is 2 plus c. So c is negative 2. Now plug that in for c. So natural log of y equals 1/2 x squared minus 2. Okay, so we've solved for c, but we need to get it so that the y is by itself. So this is the case now where you would e. And I'm actually going to leave the absolute value of y here for a second. And you have e to the 1/2 x squared minus 2. Looking at the initial condition, Plug in the initial condition. So if you plug in 2, you get e to the 0, which is positive 1. So we don't need the absolute value because we're just going to get a positive value. So we want it to be y equals positive because we're resulting in a positive output. Same thing will happen when we deal with radicals and things too, as we practice more and more of these. Sometimes you'll have a because you'll have a plus or minus. Sometimes you'll have the positive. Sometimes you'll have the negative. I'll remind you of how that works when we see those problems in the performance task. One last thing. This answer is fine. Acceptable answer. I would take this. I would stop here every time. However, if you ever go online and look at answer keys for these, they will typically start to do something. They will do this. Well, for this case, they won't. This is actually fine. We're going to leave this here. There are other problems where they can make this look a little different, but I don't think I want to do it here. Oops. So let's do one more. Come on. Let's do one more. So that was dy equals xy. The last one I want to do is dy over dx equals x divided by y. So in this case, same thing. And we'll use the initial condition of 3, 1 in this case. Okay, so same logic. We either got to multiply or divide. So we're going to multiply the y over. So we have y dy equals multiply the x over. So we have x dx. Integrate both sides with respect to its variable. Boom, boom. 1/2 y squared equals 1/2 x squared plus c. Now something I didn't mention in the last example. How come we don't put plus c on both sides? Well, the reason is if there's a c on both sides, it's not the same c. There's a different value. We can kind of just move the c from the y side to the other side, and then we have some other constant. Imagine if we did this and we had it like plus 7 on this side and we had like plus 9 on this side. Well, we could just move the 7 to the other side and end with just one constant on the right. So long story short, we only end up with c on the one side. Okay, then we plug in our initial condition here. Plug in 1 for y, so we have 1/2 equals plug in 3 for x, so we have 9/2 plus c. So subtract 9/2 over, we get c equals -4. Plug c back in at this part, so 1/2 y squared equals 1/2 x squared minus 4. Get y by itself. To do that, we multiply everything by 2, which is y squared equals x squared minus 8. Square root both sides, and we get y equals, and here's what I was just talking about, plus or minus, because we introduced square root into the problem. So which is it? Plus or minus? Can't be both, because then it wouldn't be a function, and we're finding functions. We're finding particular solutions. So how do you know is it the plus or minus? Use your initial condition. When I plug in 3 for x, I got to get positive 1, not negative 1. So it's not negative. The answer is the positive version. So always refer back to your initial condition one last time to see if the answer is the positive one or the negative one. Because had this been 3, right here when we squared 3, if it had been negative 3, 1, or 1, or I guess if it was 3, negative 1, we could have had a different result in the end. So you just have to pay attention to that. Other than that, this is pretty much the process we go through. It's called finding the particular solution. We'll do a bunch of these. Typically, you just divide or multiply, find the antiderivatives of both sides. Don't forget the plus c. Then you solve for c using the initial condition, and then you isolate y. That's it. All right, I think that's all I want to talk about right now. Okay, goodbye.